Okay, so with the final exam coming up pretty soon here, I wanted to give you guys a brief talk about what will be on it. So, you'll notice for the final exam, I don't give you a whole bunch of review problems to do because the concepts aren't the difficult part in the second half of the course. It's more, I mean, the ideas of counting, permutations, combinations, multiplication principle, that's not the hard part. It's just knowing when to do what to do. So, short of me giving you problems that are on the test, just you going and practicing problems that you find in the book or find in the um, homework set or find in the notes, or it's the same idea. So just practice, practice, practice. So let me just make sure everybody understands. The final is cumulative, which means it will cover topics from the first half of the course from that first midterm, and topics from the second half. So I like to tell you guys that as far as solving multivariable problems with and without constraints, okay, so you see that objective, Roman numeral 1, Roman numeral 2. So if we slide down here, we see what is that really talking about? Well, multivariable optimization is partial differentiation of 3D surfaces. That we don't, I'm not going to ask you, well, actually, I will probably ask you one explicit problem, just do a partial derivative. But the key here, what we're really building towards, is the unconstrained optimization and Lagrange multiplier substitution methods. I will give you one of those problems on the test. I won't tell you which type, but one will be on the test, one problem, where you're just going to have to find a partial either using the d-test if it's unconstrained. Unconstrained is where you use that d-test, which, if you don't remember, that's the f of xx times f, not f of xx, excuse me, the second derivative with respect to x, partial derivative with respect to x, times the second partial derivative with respect to y, minus the second partial with respect to x, then y quantity squared, that test. So then Lagrange multipliers, that one you didn't need to use that test, but you had to know the big Lagrange formula, which would look something like f of x comma y plus lambda times g of x y. So if you're remembering that, great. If not, probably go back and review. One problem will be on the test that covers those two ideas. There's always one duality theory problem. So either asking you just circle the next set of pivots or something of that nature. So the key is you need to be able to identify, is it standard simplex or is it a general simplex problem? And remember how you do that is just all of your answers are positive. So if you just read the problem to begin with and your answers are positive, that means you are in a standard form. If you have any answers that are negative, then you know you are in general form. So I always give one of those. And then I almost always, 99% of the time, just depending what problems I come across while I'm picking from my pool, I like to throw on an inverse matrices problem. So if you remember how we solve a problem using inverse matrices, that's putting a problem in AX equals B form and solving that out. So we end up with X equals A inverse times B. And there you go. So it's knowing how to do one of those. And the whole idea is, how do you know when you have to do those? Well, if I gave you a problem that looks something like this, let's just call it a Q, and then 7x minus 3y equals r, and I said solve for x and solve for y, you would either have to do Gauss-Jordan by hand, and that would be painful, or you could just rewrite this into standard form, or into ax equals b form, which would be 4, 3, 7, negative 3 times x, y equals q r. And now the good news is the calculator can take your A matrix and solve it for A inverse. So then you still have to do that multiplication by hand, but at least it's a lot better than trying to do Gauss-Jordan with that original matrix. So if you need help on that, go back, review that section, chapter 4.3. So for the first half material, that's the stuff I like to put on there. Usually one of each from each big idea. So you will see here that also will correlate with the ideas covered here. Did I do it in? I did it in purple. pardon me, I want to make my colors match. So solving linear programs using duality theory, purple, and then I did blue for matrix methods. I have to cough, I'm going to pause the video. So now that brings us to the second half of the class. So what we're going to be doing here is that's the first half. That was the first midterm. So second half. Now, chapter 6.1 through 6.4, if you look at that, that's Roman numeral 4. Roman numeral 4 is talking about sample spaces and events, fundamental principles of counting, so the fundamental principles of counting. Sometimes students say, what is that? Well, that's 6364. So that's permutations, combinations, multiplication principle, and addition principle. So it's really the fundamentals. It was the stuff that we used to make our building blocks, getting ready for probabilities. And then you'll notice that's 6364. Then we jump straight into 7475, 737475. So conditional probabilities and independent events. So those were kind of just your well, the conditionals weren't necessarily basic. That would be a problem where saying something like, find the probability of pulling if you're pulling 5 marbles out of a bag, find the probability of getting a pink one given that. There's your conditional when they say the given that. And then, but nonetheless, these first things all here kind of build towards your more common counting. What I like to put on the test as far as this goes is I always like to put on a few counting problems, one counting, and then I like to put on a few that are actually probabilities. Okay, so make sure you're reading. Is the problem asking me for a probability, or is it just saying how many ways? Not the likelihood of it occurring, just how many ways. So watch for that. Then there always is a Bayes theorem problem, and I always do the Bayes theorem problem the same way. And here's how I like to do the Bayes, because I try to teach you guys to do Bayes using the tree, where you have some kind of scenario, some kind of setup that might look something like this. Now, the trick here is in Bayes, the thing that makes Bayes difficult is just recognizing, is the problem asking Bayes or is it asking something else? So I always like to give part A, part B, and part C to these problems. Part A, now the order may be different, so don't think I'm telling you the order in which the problems will appear on the test, but I always ask these questions. One problem will ask the probability of A given B. The next problem or another problem will ask the probability of B given A, and then another problem will ask the probability of A and B occurring. So therefore, one of these is actually Bayes. The probability of A given B is Bayes, because you notice the order is switched. It's asking about the stem, so therefore it's a Bayes instead of the leaf. Okay, but this one, I always call it a duh, not because you should feel dumb, but because it's already given to you in the problem. So if you just kind of realize, you say, oh, they're asking me the probability B given A has occurred. That's sitting right here, so I just look at this branch, whatever this number may be. Let's just make up a number. Let's say it happens 75%. So therefore the duh is you don't do any math, you just write down the number. Then last but not least, probability of A and B occurring is the same thing as the probability of A times the probability of B given A. And so therefore you multiply straight down the branch and get your answers. So watch for that problem. It's always there. And know that you have to pick apart the problem. You have to decide which one is the Bayes, which one is the duh, and which one is just multiply down the branch. Listen to the word carefully. Likelihood of something and something occurring, no conditional probability, is the multiply down the branch. Okay, then you have the probability of B given A, and that should already be given in the problem. And then the switch, where they're telling you that the leaf has already occurred. So you say, okay, I could either be there or there. This branch is dead to me. This branch is dead to me. Oh, that's a Bayes theorem. All right, yay. I know you probably won't be that excited during the test, but nonetheless. Then as far as this stuff goes, discrete random variables, expectation, and Bernoulli trials. All right, so the key thing you need to remember when you're doing this stuff Bernoulli trials, binomial distributions, those had all the simplified formulas. So, for example, the expected value formula for a binomial distribution or a Bernoulli trial was n times p, where p is the probability of success and n is the number of trials. So, where the formula for expected value was far more complex. So, the idea I want you to kind of get across here is the expectation problems can ask, they all sound the same. You just need to be listening for, is it a binomial distribution? Is it something I can define as success and failure? Or is it something where I might have, I can't define it that way, where and success and failure with repeated trials where the probability does not change for each trial, so like throwing darts or rolling a die. I can roll a die, and then whatever I roll in the first die does not change the probability of my second roll or my third roll. So therefore, that is a binomial distribution because it's a repeated event. The probability does not change. So just watch for that. And I could define it as success or failure. So did I roll a 5 or not roll a 5? Okay. But if you need to account for every individual dice roll, did I roll a 1, a 2, a 3, or 4, or 5, or 6? Well, now it's not a binomial distribution because it's not success or failure. I hope that helps get across what's in my brain. So therefore, watch for, there will always be an expectation, an expected value problem, and it may be binomial. It may not be binomial. I don't know. So watch for that. The integration, you don't need to know how to integrate other than by using your calculator or by using the z-table. But that being said, for your final exam, I don't like you guys have to be dependent on a z-table, so I will not ask you to do any of that. All I will ask you to do is find z-scores. So therefore, I might give you all the information you need, and your job will be just to get to the table where you're going to fill in, this number here and this number here, saying my range will fall between here and there. Or if I want you to know a z-score, you're not going to need the table. I will tell you, a z-score of 1.52 equals a probability of, and I'll list it out for you so you have a point of reference, so you can do the math. So don't stress about needing a z-table. You do not need one. Nonetheless, so the idea for the final exam. I also want to point out, it's this stuff down here, the expectation, the finding standard deviations of finding and then using the normal curve. It's all a few problems. It's probably usually about 3 or 4 problems, or one problem, part A, part B, part C, part D. So just watch for that. But the key thing I forgot to mention about the probabilities. Most of the problems are usually either multiple, well, I'll say it's usually half and half. They're multiple choice, which means I will say, how many ways are there to pull a queen from a deck when you're being dealt 5 cards? So instead of putting an answer, I put how you count it. So it might say, okay, if it's what's the number of ways of getting a queen? Well, you say, all right, well, there's 4 queens. I need to choose one of them, or however you want to count it. But your answer, excuse me, there's 4 suits, and I need to pull 1. And then for the remaining cards, there are 12 suits left, and I need to choose 4 of those. I don't know, whatever the rules should be. So the idea is your answer would look something like that. That would be choice A, and then choice B would be something else, and choice C would be something else. So it wouldn't be an actual number you're going to pick. It's going to be something for counting. And do note, it's sometimes some of the problems say select all that apply, because one way of counting may work, and another way of counting may work. What I will suggest is you can, if you have time, you can always find out what the number is. And if you say, hey, this is the one that is right, and I think the answer should be 0.32, do any of the other ones come out to an answer of 0.32? And you could therefore sometimes figure out if it's a correct way of counting or not, because they achieve the same number. So it's just a little tip I like to give you guys. Let me pause one moment. I'm going to cough again. So I went back and looked over the final exam from that I gave last time, and I have covered everything that was on it. I've mentioned everything in this video. So if you have any questions, please don't hesitate to contact me. Just note my response might be a little slow as we are all fighting illness over here. So my response time is now dropped to about 24 hours. Opposed to a couple hours that I was able to do before. But nonetheless, please ask, and I'm here to help.